Okay, so in the previous lecture, right, we have seen that your what you call that power flow from line 1 to 2, ultimately it is coming your 61.4 megawatt and P13 7.1 megawatt and P32 37.7 megawatt, right, and Pg1, Pg2, Pg3 and the total load it is coming like this, and this is your delta 1 estimated and this one your delta 2 estimated, right. So, next we will go to the next slide, right. So, hold on, this because of scanning this first these two pages will come later, right. So, now we will come to continuation of this one, right. So, from the estimated phase angle, I mean it is a continuation of the previous problem, then we will go back to the previous two pages. When I was scanning, actually that two pages have been scanned before this one, right. So, from the estimated phase angles, right. So, this will be that was 60 page 65, you come to 66 first, right. So, from the estimated phase angles we can calculate the power flowing in each transmission line and the net generation or load at each bus, right. So, results are given like this. So, this is that your line flows and these are the meter W12, W13 and W32. So, P12 is 61.4 megawatt, that is F12, that is I told you F1, F2, F3, 3 lines, right, and this is the angle delta 1 estimated one 0.02857 radian, and this is the power flow 7.1 megawatt line 1 to 3, and from 2 to 3 it is 37.7 megawatt, right, and power injection here it is this is 30.6 megawatt, right, 30.6 and 7.1. So, total will be 37.7 megawatt. So, 61.4 and 37.7. So, it will be 99.1 megawatt, and delta 2 after estimation we got minus 0.09428 radian, right, and this is a slack bus. So, delta 3 is equal to 0, that we have assumed, right. So, now if we calculate the value of z function of delta 1 and delta 2, the residual we will get actually z delta 1 delta 2 is equal to your z 12 minus your P 12 delta 1 delta 2, P 12 function of delta 1 delta 2, then z 13 minus P 13 and z 32 minus F 32, and these are all square and divided by their respective meters your standard deviation square, that is variance, right. So, when we compute this, that actually the Z12 measured was given 0.62, and your here one thing it is there, that is your just hold on, this is P13, this is P1, just hold on, this is your P13, this is your P12, and this should be actually P32, although all are same. Although we have seen F12 is equal to P12, F13 is equal to P13 and P32 is equal to nothing but F32. So, this is actually P32 or F32 same, right. So, now all these things that your measure your what you call this was your measured value, that is your W12, that is Z12, that measured value. So, it is 0.62 and your P12 is equal to F12, that was nothing but minus 5 delta 1 minus 5 delta 2. This we have seen while we are trying to find out the power flow from 1 to 2, right, and also the H matrix. So, this is whole square, then your this one Z13, that is W13, the meter reading 0.06 minus your it will be 2.5 delta 1, because P13 is 2.5 delta 1, that is whole square, plus your it is your this is your Z32, right. So, 0.37 and this one is minus your F32, that is your minus 4 delta your this thing what you call this P your P32, that is I told you that F32 and P32 are same. So, that there also you will get that your it is actually minus 4 delta 2. So, it is minus minus plus. So, 4 delta 2 square divided by their respective your here it is variance sigma 12 square, sigma 13 square, sigma 32 square. So, all these things are divided. If you do so and compute this one, delta 1 delta 2 means these are all estimated value, these are all estimated value, right, these are all estimated value, right, these are all estimated value. So, all estimated value. So, whatever you have got you substitute there and ultimately you will get that your J delta 1 delta 2 will be 2.14, right. So, that is the residue. So, with this now question is that suppose the meter on W13 transmission line was superior in quality to those on W12 and W32, right. So, how will this affect the your estimate of the states, right. Intuitively we can reason that any measurement reading we get from W13, that is right, will be much closer to the true power flowing through line 13, right. Then can be expected when comparing W12 and W32 to the flows on lines 1, 2 and 3, 2 respectively, right. Therefore, we would expect the results from the state estimator to reflect this if we set up the measurement data to reflect the fact that W13 is a superior measurement, right. To show this we use the what you call following your metering data. For example, I will come to that previous 2 pages. First, say W1 and W32, suppose it is 100 megawatt full scale reading and plus minus 3 sigma is the megawatt accuracy. That means it is 3 megawatt means plus minus it is 3 sigma. So, sigma is equal to 1 megawatt, that divided by 100, that will be 0.01, right. That is their standard deviation. Now, meter W13 is 100 megawatt, but its accuracy is plus minus 0.3 megawatt, right. Therefore, sigma is equal to 0.1 megawatt, that means 0.001 per unit. So, sigma actually your here it is very small, that means meter 13 is more accurate than meter your 1, 2 and 3, 2, right. Now, the covariance matrix to be used in this least square formula, now it becomes actually that R is equal to sigma, directly I am putting W12 square sigma W13 square sigma W32 square. So, basically in this case it will be your what you call 10 to the power minus 4, 10 to the power minus 6 and 10 to the power minus 4, right. That will be my R, right. And then we now solve equation 23 again with the new R matrix. So, that R is changed, rest are remain same for the problem, right. So, this is your H transpose, this is your R inverse, this is H, right, into this is your H again and this is R inverse and this is completely whole to the power inverse, right, and this one and multiplied by this measured value 0.62, 0.06, 0.37. Now, if you compute this one, you will get this is your delta, this is your delta 1 actually estimated, this is delta 2 estimated, right. You will get 0.024115 radian and delta 2 estimated you will get minus 0.097003 radian, right. Therefore, if you now calculate the power flow using the same thing, then you will get that W12 power flowing from 1 to 2 actually, that whatever meter reading was given, that 60.55. Simply you can calculate this one, right, directly you can calculate delta 1 minus delta 2 upon x12. Only thing is that all this bus voltage magnitude we have assumed 1, right, 1 per unit. So, similarly here also your delta that power flow from line 1 to 3 sorry, it is actually 6.03 megawatt, but look its meter accuracy is very I mean plus minus 0.3 megawatt. So, sigma is equal to 0.1 megawatt. So, accuracy is I mean quite good, that is why it is very close to the meter reading, because meter reading was given for this meter W13 was 6 megawatt. So, it is coming 6.03 and similarly W32 according to these calculations 38.8 megawatt. So, similarly you can find out that what what will be your total 60.55 and this side 38.8. So, it will become 99.35 megawatt, right, and delta 2 is equal to this much and delta 1 estimated is this much, that we have done it. And similarly here 6.03 coming and 32.77 is coming. So, it is 38.8 megawatt, right. So, with this your what you call that with this this is this shows that how one can your what you call estimate that angle delta 1 and delta 2. Now, I will go back to this that your this is equation 29 is okay, but we will go back to that your other two things, that is your these two, right. So, there is also a closed form solution. So, first you will go to this, then you will come is 65A or 65B, the two pages, right, because I scanned it before. So, there is also a closed form solution to the problem when n is greater than n m, that is your underdetermined, right. Although, in this case we are not estimating x to maximize a likelihood function, since n is greater than n m, right. So, usually implies that many different values of x estimated can be found, right, and that cause actually f I x estimated to equal to z I measure for all I is equal to 1 to up to n m exactly, right. Rather, the objective is to find x estimated such that the sum of the squares of x I estimated is minimized, right. That is, you minimize your I is equal to 1 to n s x I square, and that can be written as x transpose x. So, this is equation actually 25, right, subject to the condition that z measure should be equal to h into x. This we have seen earlier, right. The closed form solution for this case will be x estimated will be h transpose inverse into z measure. So, this will be the solution, but question is that if time permits I will derive it for you, right. But let us see, right. So, from that equation only slight change will be there and it can be derived. So, this is equation actually 26. So, easy to remember actually h transpose then into h transpose inverse into z measure, right. And in power system state estimation, your underdetermined problem, that is when number of state variable greater than number of measurement, right, are not solved as given in equation 26. So, we do not solve it like this, right. So, rather pseudo measurement are added to the measurement set to give a completely determined or over determined problem, right. So, these are the things, if time permits we will see that, but question is that time will not permit to solve on this problem because it takes time, right. So, that is all there, right. So, again we will go back to your next thing. So, whatever little bit we have seen, that is particularly suitable for your DC network or DC circuit, right. So, and all these examples that two different data I showed you that how it works. Now, we will come to state estimation of an AC network, right. In the AC network sorry, that power flow in any line, this it is actually a nonlinear function, right, because that cosine and sine terms are involved, and similarly that power injection also it is nonlinear because sine and cosine terms are involved, right. So, question is that how one can develop this method for state estimation of an AC network. So, in this case philosophy will remain more or less same, but mathematical development will be different, right. So, now in the least square calculation, right, we are trying to minimize the sum of the measurement residuals. So, we know that minimize your jx, that sigma I is equal to 1 to nm is the number of measurement, right, that is into your here bracket z I minus f I of x, because x is a vector, right. So, it is function of so many state variables, right, square divided by sigma I square. Actually this is actually this f I for I, right, it is function of several, it is actually I am written in a thick x, right. So, that is actually f I, it is function of x1 x2, right, your xns, right. So, that is why it is actually given like this. So, in the your case of a linear system, the f I x we have taken f I x is equal to h x, we have seen, no, h I 1 x 1 h I 2 x 2 like this, right, are your themselves linear, and we solve for the minimum j x directly, that we have seen, right, when you took that function f x is equal to h x. Now, in an AC network the measured quantities actually are megawatt, megavar, then megavolt ampere, amperes, transformer tap position and voltage magnitude. So, so many your what you call the measurement quantities are there, and depends on which one you are trying to estimate, right. So, I mean line flows or power injections or other voltage magnitudes or its angle, right. So, the state variables are the voltage magnitude at each bus, right, the phase angles at all but the reference bus and the transformer taps, because at reference bus means that is a slack bus that we need not estimate, and the transformer tap position, right, that also can be considered as a state variable. So, the equation for power entering a bus is not a linear function of the voltage magnitude and phase angle at each bus, that we know for AC network. Therefore, the Fix function will be nonlinear function except for a voltage magnitude measurement, where Fix is simply unity times the particular Xi, right, that corresponds to the voltage magnitude being measured. So, for megawatt and megavar measurement, right, on a transmission line from bus I to bus j, we would have the following terms in Jx matrix. So, that actually this that power flow from bus I, that is from bus I to bus j, right. So, this I have used this expression, right. It depends on your which convention you are taking regarding Gij, negative or positive, it does not matter, final result will remain same, right. So, in that case what one can do is that this is my say power flow, that your power is flowing from I to j, you can measure, right. And another thing is that you have to also find out that what is Ei, your what you call that your mathematically or whatever is expression, that is Pij, the power flowing from line I to j. So, one small thing, that suppose this is my line 1, suppose forget about this, suppose this is my bus 1, bus I, and this is my bus j, say this is j, this is I, right. I have a meter here, say it is called Wij. If you put a meter here also, say Wji, right. So, if you put in just near the bus this meter to measure the power flow, so line has resistance R plus Jx, say direction of the power flow is like this, right. So, in this case whatever power you are flowing, you will measure near this bus, I mean in the line near this bus I, right. So, if you try to measure here, that it will not be same, because line has R, so it has the loss. So, whatever it will measure here, it has that loss will be excluded. That means, if you assume that lossless line, that is R is not there, then this reading and this reading you can take same, but line has loss. So, whatever reading it will be there, whatever reading of this watt meter, the direction is this way, right. So, it will be this one minus your what you call that power loss in the line, that is I square R will be subtracted, that will be the meter reading, right. So, similarly, when you measure power, right, megawatt Ij, you have to see that you have your what you call place the meter near in the line near bus I, right, and that is your megawatt Ij measure, right. Similarly, minus this power flowing equation, power is flowing from bus I to j. So, I have used this your what you call this equation. So, that is Ei square Gij minus Eij in bracket Gij into cosine of delta I minus delta j plus Bij sine of delta I minus delta j, right, whole square, this is whole square, right. So, because we have to take the residue, right, divided by sigma square megawatt Ij, that means the meter which you have placed near the your near bus in the line Ij near bus I, right, that accuracy also is given. So, that is your standard deviation. So, sigma square megawatt Ij. So, this is actually equation 31, right. So, next is, and similarly if it is a megavar, then it is megavar Ij, that is your measured value, minus Ei square minus of, this is actually minus, another minus is here, right. So, minus in bracket minus Ei square Bij plus B cap Ij, because line I and j you have charging your capacitance, that means you have the charging susceptance, right, that also need to be taken care of. So, that is why Bij is there plus B cap Ij, this notation I have used, right. So, if you treat it as a pi network, then you have accordingly you have to your what you call, you have to take that values, right. So, that is why this Bij plus B cap Ij is taken minus Eij in bracket Gij sin delta I minus delta j, then minus Bij cosine delta I minus delta j, right. So, your what you call another thing is, if you in the line also you may have that your, if it is a series compensated line, say transmission line, suppose series capacitor are there in the line, then also that your what you call that reactance also you have to consider, right. So, all these things you have to consider, right, for when you are measuring that your what you call that your megavar power, that is your reactive power, right. So, all these things you have to consider, that is why this B cap j is also added here, right. So, so this is actually your what you call that that reactive power measurement, right. So, then whole square, because residue you have to take divided by that meter which you are using for measuring the megavar. So, sigma square megavar I j. So, in the case of real power no need to consider any your what you call that shunt or series capacitors or anything, right. But when you are trying to find out your what you call that your reactive power, when you are measuring a mathematical equation, that if series compensator line, then you have to also consider that your what you call that your capacitive reactance and the susceptance, right. So, this is actually your megavar I j. I mean this way you can put in mathematical form. So, next one is that if a voltage magnitude measurement would result in the following term in Jx, that is it is E I measure, of course, is magnitude minus E I whole square by sigma E I square, because you are measuring the voltage magnitude. So, measured will be there and this minus E I square to sigma E I, right. So, from this one you have measured, but from where you will get your what you call E I. So, you have to run, you need to run that load flow, right. So, similar functions can be derived from MVA or ampere measurement. If you want to measure MVA or if you want to measure the current flowing through any branch, so that ampere measurement, right. So, now if we do not have a linear relationship between the states, right, that is your E values and delta values and the power flows on a network, we will have to resort to an iterative technique to minimize Jx, right, because that I mean ultimately this term, that equation 33 and equation 31 and 30 or what you call 32, right, these terms are non-linear. So, to make this term to 0, right, I mean you have to make your what you call to minimize this objective function. So, it is not a linear. So, direct solution is not possible. So, we have to go for your iterative technique, right. So, therefore, a commonly used technique for power system state estimation is to calculate the gradient of Jx, right, and then force it to 0 using Newton's method. That means, what you have to do is the Jx is actually a nonlinear function, you have to take its gradient, right, and then iteratively you have to force the gradient to 0. That means, you have to make that gradient to 0, you have to go for your what you call iterative technique. So, I will show you how it is, right. So, here we will review how to use Newton's method on multidimensional problems before proceeding to the minimization of Jx, right. So, suppose given that function, suppose you have a function Gix, right. So, you have a function, say it is Gix, right. Gix means it is a thick x, that is your Gi function of x1, x2, right, this up to xns, right. So, this is actually Gi for I is equal to 1 to n, right. So, we wish to find x that gives actually Gix is equal to Gi desired value. I mean this is actually we want that when that solution will converge, right, for we have to obtain the your different values of x, right, x1, x2 like this, such that whatever desired value we want it will give, right. So, if we arrange the Gi function in a vector, we can write like this, just hold on, that we can write like this. That means this one we can write G desired minus Gx is equal to 0, right. So, this we want actually that Gx should be, I mean when it will convert, Gx should be is equal to G desired. So, by perturbing x we can write that, suppose you make perturbed x, right, from say some initial value initially x0. So, now or initially it was x, say I have written like simply x, right. So, G desired will be there, that is your specified, right, we know that, minus G then x plus delta x, right. And therefore, the G desired minus your G x of delta x, x plus delta x, you can write G desired, then you can do this term, you expand it in Taylor series, right, that is G desired minus G x minus your G dash x into delta x, right. So, this way only up to first order term, we are ignoring that your higher order terms, right. So, this way you can make it like your in Taylor series. Therefore, where we have expanded that your Gx plus delta x in a Taylor series, about x and ignored all higher order terms, right. Therefore, the g dash x term is Jacobian matrix of first derivatives of g x. Then what we can do is that this equation that this equation that g desired minus g x minus it is equal to 0. Therefore, if you look into that, then this equation you can write, I mean this equation it is equal to 0, right. Therefore, this equation, so in bracket I am just writing g dash x, right, delta x is equal to g desired minus g x, right. This is the thing. Therefore, delta your what you call delta x will be g dash x your what you call inverse, then g desired minus g x, right. Therefore, your this term delta x can be written as g dash x inverse, right, into g desired minus g x. This is equation 36. That means, what you have to do is that when you will start with some initial values, right, when you start with some initial values, then every time that you have to force that your what you call g x should become g desired, right. When g x is equal to g desired, right, then what will happen, that solution has converged, right. At that time delta x will become 0. So, in that case, first you have the function g x, take its derivative and try to iterate, and in general that you have to update x is equal to x plus delta x in every iteration. That means, that in general that you have to, when you later we will see that we have to force the gradient to become 0 iteratively, and if say our g desired say is equal to 0, right. In that case, what will happen, that delta x will be nothing but g dash x inverse, right, and if it is g desired 0, then it will be multiplied by minus g x, right. So, if g desired is 0, right. So, that is why we are writing this one, right. Note that if that is why I have given, if g desired is identically 0, then we have delta x is equal to g dash x inverse into minus g x, right. So, this is equation 37, right. Thank you very much, we will back again.